Okay, good evening everyone. Welcome to the Astronomical Society of Edinburgh. If you're a visitor, you haven't been before, especially welcome. I see we have some old friends coming back, Horst from Germany, good to see you. Hang around afterwards, chat to us for some tea and coffee, and carry on now. This is what we've got coming up. My name is Mark Phillips, I'm the President. I've got a few news items just about what's going on in the Society, what talks we've got coming up in the next few months, and then the main event of the evening we have talk about the Square Kilometre Array from Dr Tyler Bourke. Sean will be doing the sky in October. He's remote, he's in Ireland, so hopefully he's doing the sky in Scotland and not the sky in Ireland. It's probably very similar. And then we've got the tea and coffee and chat afterwards as well. Just a reminder that Alan Pickup's Sky Guide for October is on our website, and it's got a section in there on Comet Shushin-Chan Atlas, which could be impressive over the next few weeks. And if it is impressive, then we're going to claim it for our centenary comet because it's our 100th birthday in a week's time. So it is actually ours. Our outreach events last weekend went really well. We were doing some solar observing and general helping out at the Royal Observatory in Edinburgh. As you can see, we did actually get a bit of sun, although the woman looking through the telescope there is actually looking at a picture of the sun that was in the observatory that Horst put up there about 10 years ago, so it wasn't actually the real sun, but it was really good. Will and a few other people were up on Collective on Carlton Hill showing people the Cook telescope, doing some tours there. That went really well as well. So thanks to everyone who took part in that, especially Will and Peter for organising it. And it really is good fun, so if you haven't done it before, consider doing it next year. It's worth doing. Thousands of people come through, and it's good fun chatting to them all. For members, as you know, if you haven't heard already, then I don't know where you've been, but we have our 100th birthday on the 15th of October, and this is for members only. We are at the Royal Society of Edinburgh, and the food and drink will start at 6:30, and then we'll have talks from 7:30. And we have Professor Chris Lintott of Sky at Night fame as our guest speaker. And you'll get a lot more information by email over the next week, so keep an eye on that. We have closer tickets for that, but if you're new to the Society or you missed out for whatever reason, then let me know and we'll see what we can do. It will be on Zoom for our members and recorded. We don't know what all the jobs are for the evening yet, but we will have a few things we need help with, so if anyone would like to volunteer, then chat to me or to Jim, who's on the tech desk, and it'll be useful to have a few people around who are ready to jump in as needed. Nothing too onerous there. Hopefully you've been seeing these articles by Bruce Vickery. I've been putting them in the newsletter, and they're on our website. These are short articles on how astronomy developed in Edinburgh, and I think they're really excellent. Bruce is really knowledgeable, and I think they're just the right length just to get an idea of our history. We're up to part 10 now, Piazzi Smythe's interesting interest in pyramidology, which is a bit colourful. But it's useful at this time because it puts our own historical context, puts our own history into context at the time as well. But you can find that on our website, all the articles, and I think they're really good. And a reminder that we have our own history that Randall Stevenson's written for us, from a lot of material that Horst put together, and that's on the members' website, and it's a really good story, very readable. So if you haven't seen that yet, I would go and have a look at that. But we will be using some of it at the centenary event week on Tuesday. Also for members, our next image of the quarter competition is ready. Images taken July, August, September. So email me the usual presidential address, and you may submit up to 3 images, and you can use data for one of them from our telescope in Spain, but only one of those. And Sunday night is the deadline, so if it doesn't get to me by midnight Sunday, then you missed out. But the details are in the newsletter. That was last quarter's winner from Ramza Bekaida. Over the next couple of months, we have our Imaging and Observing Group meeting on next Wednesday, 9th October, and that's on Zoom. On the 15th of October, we have our centenary for members. The next in-person meeting is on the 1st of November, and that's here. and will be on Zoom for members and YouTube for visitors. That's about the Slow and Digital Sky survey from Dr. Anne-Marie Wymans from St Andrews University. We've had this one lined up for quite a while, but it's always been rescheduled for various reasons, so we're looking forward to that one. On the 15th of November, this will be an online-only talk from Dr. Joe Barstow about how to be an explanatory detective. And then back here again on the 6th of December with our own Dr. Rebecca Higgett, about a nice historical talk about the Early Dial and the astronomical interests of Archibald Campbell, Earl of Early. Okay, that's it from me. So give us a second and we'll change over to our speaker for the evening, Dr. Tyler Bourke. Yeah, that's fine. Yeah, okay. Yeah, okay.
Just have to wait a second while the computer thinks about joining. There it is. All right. Okay, well, thank you for inviting me to come and speak to you. As you said, my name's Tyler Bourke. I work for the Square Kilometre Array Observatory. Makes sense. I'm a senior scientist there and also a project scientist for the telescope. So the scientist part means I get to do some science. I've been around a long time, and the project scientist part is actually the details of the job I do, working with the engineers and the other people within the project to make sure they build telescopes to do the science we want to do, not just something they think is nice engineering-wise. Okay, so as introduction, I'm going to try and motivate you now to why we do radio astronomy for a bit. So in the background here is this beautiful image of the Milky Way down south. In the front is an image here of the part of the Meerkat telescope, which is a radio telescope array in South Africa. It's being built on the site where we're going to build the telescopes for the Square Kilometre Array. Now, it obviously doesn't see the sky like this optical image, but we'll get to that in 1 second. Okay, so here's our Milky Way, the center of the galaxy, the plane of the galaxy. So what you see here is not just the stars in the background, but all the gas and dust blocking the stars in the foreground. Okay, so we're in the plane of the galaxy. We can't see everything. A lot of its starlight is blocked, unfortunately. In the center of that galaxy, the stuff that's in the orange in the background is actually towards the center of our galaxy, the center of the Milky Way, where there's a supermassive black hole. It's about 10 million times more massive than the sun. Okay. If we could go above our galaxy a little bit, instead of being stuck in the plane, it would look something like this. Okay, this is the Andromeda galaxy, M31, sort of our sister galaxy in terms of size and mass. And again, you can start to see the dark lanes in this image, okay? And you can also see a lot more stars through this. But now you can see that there's layers, so that's the arms of the galaxy. And if you go right above or below the galaxy, I like to use the below perspective, being from Australia and the southern hemisphere, it would look something like this. Now, this is obviously an artist's conception of what our galaxy looks like, but this is based on real data of our galaxy, so it's not just something that made up. It's actually the idea of a bar in the middle there and a couple of major spiral arms and some smaller spiral arms. So this is what we think our galaxy looks like. And to put that in perspective, there's the size, 100,000 light years across. And this is sort of where our sun sits, a bit more than halfway out, sort of in the suburbs. So there's a lot of stuff between us and the center of the galaxy and all the other arms. So we don't get a great view, but that's sort of where we are. So not just the plane of our galaxy, but here's now an all-sky image from the Gaia satellite, which is a magnificent little satellite that actually observes stars over and over to trace their motions and can make these beautiful images. And so now we see the plane of the galaxy in there. We see the large and small Magellanic Cloud down to the sort of bottom right there. And you can see that some of the stuff comes way above the plane. That's the stuff that's nearby to us. But then there's all the plane of the galaxy. Now, if we just take that and now turn on our radio eyes, it looks something like that, at least at 400 megahertz. So it's a little bit different, but a little bit the same at the same time. Okay. should I try and point? All the people online probably can't see. But if you just go back and forth, should I try and point, or is that not a good idea? Okay, very good. Okay, this one. So you see the Magellan Clouds here, okay, and then you see the center of a galaxy here, and you see some blotches, whatever, there's some stuff there. But then if you look here, there's different stuff, and same stuff. There's the Magellan Clouds again. There's something bright here. There's something bright there. This is Centaurus A galaxy. If you just keep an eye on this sort of spot here, so go back. Oops, too far. There's nothing there. It sort of sits here, okay? So already looking with the radio, you see different stuff. So it's complementary, but also new to what we see in the optical. Now if we just focus in on this, on the plane again, okay, so on the next slide, I'm going to show this cutout of the center of the galaxy, of the plane of the galaxy, sorry. This is it in a multi-wavelength view, this beautiful poster put out some years ago now by NASA. So this red box in the middle and down near the bottom is the optical that I just showed. At the very top is the same field of view that I showed at the radio wavelengths of 400 megahertz, okay. The top four panes here are all radio wavelength observations. So they have the hydrogen at 1.4 gigahertz second from the top. It looks different to the 400 megahertz. The radio at 2.5 gigahertz also looks different. So it's about 5 or 6 times longer, higher frequency, shorter wavelength. And then the molecular hydrogen also looks a bit the same but a bit different. The middle three are infrared images that tracing different amounts of heat radiation. The near infrared, you really start also pick up the stars, so that's sort of just off the optical, and we can actually sometimes observe that from the ground about 1 micron. And then you get down further to even higher energies, X-rays and gamma rays. All complementary, all useful information for us to understand what's happening in this case in our galaxy, but all throughout the universe. So this is to highlight the areas that SK will observe, those top 3 areas. Hopefully you've all seen the great images coming out from the James Webb Space Telescope in the last few years, and that sort of does that mid-infrared area there. We've certainly seen the great images from the Hubble Space Telescope over many, many years now, and that's what operates in the optical and the near-infrared. And then what we call the ELTs, these extremely large telescopes that are now either in design phase or being built, in particular, the one being built by the European Southern Observatory in Chile, which will have a mirror of about 39 meters. And then X-rays and gamma rays, you can't see them from Earth, so you have to put up satellites in space to detect that emission. Now, radio is excellent because we can do it from the ground, okay? Now, these 2 plots here sort of show you the transmission of light, or in this case, electromagnetic radiation, through our atmosphere, okay? So on that top plot there where it says 100%, we can't see through that. It's totally opaque, okay? We want to have that number be as low as possible. And that happens in the optical, so you can see the rainbow there from the optical emission. There's some little spots there in the infrared that gets through, but then in the radio, it's completely open. We can see right through, there's no problem. And that's great, we can do stuff from the ground. As I mentioned, gamma rays and X-ray satellites are up there in space. And a lot of infrared satellites are best done at space. That's why James Webb is pushed way out from Earth, pointing away from the sun. Now, if we just look at the radio part of the spectrum by itself, we can see there's lots of stuff going on, and we sort of divide up into bits, right? 1 meter, 10 meter, 100 meters, or 3 megahertz, 30 megahertz, et cetera, et cetera. It's sort of just convenient for us to talk about the radio spectrum. But you can see there's a lot of emission in there. Our radios, okay, AM and FM radios. Wi-Fi comes in there, GPS, mobile phones. It's good things in a lot of ways, but for radio astronomers, bad things. And then sort of radio astronomy, at least in this cartoon image, is sort of stuck on the end there, where not much is happening otherwise. So a lot of the stuff at the very low frequencies, it doesn't really affect us doing astronomy on the ground because we can't observe through atmosphere anyhow. The radiation just bounces off to the electrons in the Earth's atmosphere. SK sort of covers that box that I've indicated there. So that radio telescope on the end there is at a higher frequency. That's what the millimeter astronomers do. So there's a telescope in Chile called the Atacama Large Millimeter Array, and that's where they observe. We're observing at lower frequencies. And as you can see, I just mentioned, there's a whole bunch of problems in there. So mobile phones and the GPS and the Wi-Fi, et cetera, cause us a lot of grief. Even more so recently with the idea of putting up these constellations of satellites to provide service, Wi-Fi, everything all across the world. That's causing us a lot of problems. All right, so let's have a look at some of the actual images from radio wavelengths compared to what we see in optical and elsewhere. So this is an absolutely fantastic image of Jupiter from James Webb Space Telescope, okay? That's just amazing to look at. You learn a lot of information going to infrared from the optical. But if we also observe in the radio, we learn something else, okay? So there's the great red spot in the bottom image when it was red. I don't know what color it is right now, but when I was doing my mostly amateur astronomy days, it wasn't very red, unfortunately. And in the top image is in that same area observed with a very large array in the United States, okay, at frequencies of 12 to 18 gigahertz in blue and 8 to 12 gigahertz in yellow, at wavelengths of 2 and 3 centimeters. And I'll put in here, this is also a frequency that SK will observe. I'll mention that later on. Now, the radio observations are great because they're not seeing the top of the clouds, which we're seeing in optical, but they're observing 100 kilometers below the clouds, and you're still seeing the spot, the great blue spot in this case. Okay. So you learn more information about what's happening at the different layers of the atmosphere, at least in Jupiter, by going to radio wavelengths. This is an optical image, two optical images of the same same idea. One's just a nicer, higher resolution version of the giant galaxy M87. This has been in the news because it's one of those two galaxies where we've imaged the black hole shadow, okay? But this is a much wider view. This is showing the jet coming out from the center of the galaxy. And the optical is great, okay? So that little box in that top image there is the same as on the other one. So that little white box is the optical image. This little box here. And then we've zoomed in here to show that same, let's zoom in on that. So it's the same optical image, great. But then, if you zoom in on this little dot right here, with radio wavelengths, you see the base of the jet, basically. You see all this stuff coming off. And this is a very early, low, well, this is difficult to do back in the day, so this is not a great image, but now we can do much better. So again, we have the optical image up the top here, and we zoom in on this little dot, and that's what this is. This is now an image at higher frequencies with the ALMA telescope. Zoom in again. This is sort of similar to the image I just showed before in the radio with all these, this structure is all real. And then zooming in on the center, you get the black hole shadow. If you just look at it at different radio frequencies or wavelengths, you can zoom in, zoom in, zoom in, zoom in. You can't do that in the optical and infrared. You learn more information on the jet the more you zoom in, right to the black hole. So that's great. So what I've been talking about mostly is this the top image there, the radio continuum at 400 megahertz or frequencies also that are the continuum emission. So in this case, it's emission from electrons just moving through magnetic fields, giving out continuum radiation. In the middle there is a very specific radiation given out by atomic hydrogen, and we know that hydrogen is the most abundant element in the universe, so this is important for us to understand and to study. Okay. And it gives a radio wavelength, it gives a very distinct signature at 1.4 gigahertz. So I've shown this all-sky image again at 400 megahertz. And then, if this will work for me, there we go. That's that same sky in the atomic hydrogen line. And it's also color-coded by velocity. Because this is a spectral line, we can use how the line center frequency shifts due to the Doppler effect to also code that as a velocity, as a gas moving towards or away from us. And so you already see that, unfortunately the center part here, the very center is washed out in the scaling this image, but I don't know if you can read the scale down here, but you probably can't. Well, yeah, this is 200 kilometers per second to minus 200 kilometers per second. Kilometers per second, that's a lot. So what you see here is the two Magellanic Clouds. They've got their own very high velocity compared to our own galaxy, and there's also velocity information being traced here. Also important information to us to understand the energetics within the gas in our galaxy and in other galaxies. All right, so let's just discuss this hydrogen atom for a second. What does that mean? So I've already mentioned this abundant element in the universe. It has a primary transition at 21 centimeters. Where's that come from? Well, a hydrogen atom is simply a proton with a neutron going around it, and there's this quantum number called spin, and either the spin of the proton and the electron are considered to be aligned. They're in a higher energy state, and when it flips, when the electron flips 180 degrees, it's in a slightly lower energy state. It can't be anywhere in between. It has to be one or the other, up or down. Okay, and that's what sends off this emission at 21 centimeters. So each hydrogen atom will do this every 100 million years. So you think, well, how can we observe this? Well, that's because there's so many atoms that there's always one of them, or many more than one of them, actually making this transition. This is a great discovery because this was discovered actually by a PhD student in 1951, and that's him with his little instrument sticking out of a lab at Harvard University, out the window basically. There are a few groups trying to observe that at the same time. I think that's kind of Nobel worthy, but it didn't win a Nobel Prize, but it's a great discovery. And so by using this transition, this has a very fine frequency, and then observing it, as I said, to see how the frequency shifts as the gas moves through the Doppler effect. I hope everyone's familiar with the Doppler effect, at least from the sound, where in this case you have this example of an ambulance coming towards you and moving away from you. It could be a train engine, it could be anything, and you hear the pitch will change, okay? It's a different pitch coming towards you and different pitch going away from you. And when it's coming towards you, the waves are all compressed, and when it's going away from you, they're stretched out. And that's basically the Doppler effect. And then when we observe that in a galaxy, so on the right here is this sort of cartoon picture of a galaxy. The center is B, it's spinning around, A is spinning towards us, C is spinning away from us, and the line is shifted, and we can trace that emission. That's very important for us as radio astronomers to trace this, any emission actually. Hydrogen's the best one, but there are many other atoms and molecules we use, and they have the same effect. I very much like this cartoon to show exactly how this works. So on the left there is the pinwheel galaxy M33 in stars. In the middle it shows it in stars, and the blue purpley stuff is the hydrogen emission, but in this case it's not color coded, it's just the emission. But on the right is the color coding. And what you really see here is this galaxy spinning. So the blue shifted emission at the top and the red shifted emission at the bottom are the extremes. The blue shifted coming towards us, red away from us, and the whole galaxy. So you can use this information to determine the mass of the galaxy just by how the gas moves. And I should say that by doing that some number of years ago now, that's how we just basically discovered dark matter. You can trace and you couldn't do that with the stars. You needed to do that with other wavelengths to really show this was really happening, because the stars run out of emission, but the gas keeps going. And we could see that the velocities of the gas weren't following what we expected from normal sort of Kepler's laws. The velocities were still growing or staying constant out to very large radii. And that meant there had to be extra mass that we couldn't see, and that's where the dark matter came from. All right, so going back, as you can see, I like to look at our pictures of our galaxy here. Here's a little red box at the center of our galaxy. It zooms into the bottom left there, another optical image of that same piece of sky. And then another little box where you zoom in, and so the two images on the right are the final zoom. They're the same field of view. At the bottom is the optical image of the center of our galaxy, or looking towards the center of our galaxy. And as I've said before, you don't really see much. With one of the fantastic new telescopes out there, this Meerkat telescope, which I showed on the very first slide, is an image at 1.4 centimeters, so kind of the hydrogen line. But this isn't the hydrogen emission, this is actually continuum emission. So much structure going on, so much information that we could use as astronomers from this image. So the center of our galaxy is here. These are some magnetic streamers somehow feeding into the center of our galaxy. Some of these are supernova remnants, some of these are star-forming regions. There's also these weird magnetic filaments up and down here. We don't see any of that in the optical, so we learn a lot here. Try and understand what's going on has been a big challenge. And there are just color-coded, just to reference, and you can see the supernova remnants marked and some of the key features. This is a beautiful image. Just some more images, some rogues galleries here. So at the center of this is an optical image of the radio galaxy, Hercules A. but it's an optical image, it's kind of a boring blob, but there's these two fantastic jets being spewed out from it at relativistic velocities, okay? And they are much larger than the galaxy itself. This is crazy stuff. Centaurus A, I mentioned that before on one of the slides. So here on the left is a beautiful image with the dark lane. It's another rather large galaxy. And then you zoom into the center of the galaxy, and again, you see these beautiful radio jets coming out from the massive black hole at the center, supermassive black hole. And I think this is finally, but here on the left we have a group of galaxies, the M81 group. There's 3 of them there, including M82 at the top with the red stuff coming out. It's a starburst galaxy, very active star formation. You can almost see in this deep image a hint that maybe they're connected. There's this stuff floating around. But if you look at the hydrogen emission there on the right, just color-coded without the velocity information, you can definitely see that they're interacting, tidally interacting. Especially the bottom 2, there's certainly something happening there. And this is what we say, in the optical we see a universe of stars, but if we look at hydrogen, we see a universe of hydrogen, and they're complementary but also different. All right, so hopefully that's motivated you to say, yes, we must go and observe radio wavelengths, Tyler, let's do it. Okay, well, let's do the SKA then. I just put out a mission statement here. So, there's 2 things in this. One is for us to build cutting-edge radio telescopes. And the other thing that's become a big part of our mission is to deliver benefits to society through global collaboration and innovation. And that's particularly important for in our 2 host countries, as we especially work with Indigenous people in those countries. Now, the science motivation is to study the history of the universe in hydrogen. Okay, and by designing a telescope that does that and making it an observatory rather than an experiment, we can enable transformational science in many other areas. So let's look at some of those. So this is sort of a headline list of the science areas, okay? The top 2 there, so we're building SK in 2 parts. Phase 1, smaller, get it going, show we can do it, and then hopefully expand to something really bigger. The first phase is going to focus on testing general relativity and observing the cosmic dawn. So there's all this other great stuff we can do there. I'll come back to this, actually. So what is the SKA? Okay, so we're one observatory, but we're 2 telescopes, and we sit on 3 continents. Okay, so the headquarters is at Jodrell Bank near Manchester. Hopefully some of you have been there. That's where I work. And the 2 telescopes we call SK Mid, because it observes in the mid-frequency radio range, and SK Low obviously observes in the low-frequency radio range. And Mid is based in a desert area called the Karoo in South Africa, and Low will be based in the outback in Western Australia. Mid will have about 200 dishes, each about 15 meters across, spread over 150 kilometers. And Low is 131,000 basically antennas with log periodic antennas. There'll be a close-up of them later on, but each of these antennas in this image is about 2 meters tall. And they're spread across, at this point, 74 kilometers. Actually, as soon as this image is up. This is obviously an artist's conception for both of these, but in this image, these are what the SK telescopes will look like. But these are the Meerkat telescopes that already exist on site. So the Meerkat will become part of the SKA in a few years' time. And the big grand plan is to always have a much bigger telescope, so 2,000 or some large number of dishes across South Africa, and 500,000 more antennas across Australia and maybe into New Zealand and other Southeast Asian countries. All I want you to take away from this is that we have many member countries involved. All the countries on the right there are listed. They're already full members, starting from Australia through to the UK. And a bunch of other countries are in various stages of joining. France and Germany are pretty close, and a few others. So it's very much a global effort. You can't build these big facilities by yourselves anymore. Countries can't do this alone. We do require this partnership of science. Right, so there's Jodrell Bank. That's our building in the foreground. And the telescope sites, so SK Mid in South Africa. The green dots here shows the layout. So each dot is a telescope. It's set out so that about half the telescopes are in a central region about 1 to 2 kilometers across, and the rest go along these spiral arms out to 150 kilometres. Okay. And you can see the first dish there, a couple of images of the first dish being erected earlier this year. So this is hopefully the first, if it performs well, it's the first of the many, and 2 or 3 others are already going up on site. And then in Australia, we have the low telescope. As I mentioned, these antennas, right? So basically, they're just simple antennas. This structure here means you're observing different frequencies, from very low frequencies to the higher frequencies. And as I said, they're about 2 meters tall. What we do is we group them into stations. So we have 256 of them in a station, which is about 35 to 40 meters across. So each station acts like its own telescope, and then we have an array of telescopes. So you can see a couple of the image there with the sunset is a demonstrator, and then the artist's conception below that. Hopefully you're asking yourself, well, why you have an array of telescopes, Tyler? Why just to put one big one out there, you know? At least at radio wavelengths, it comes down to size and engineering. We just can't build them that big. To observe these very long wavelengths, we need very big telescopes, and they just can't stand up to the pressures of gravity. So we build arrays, and this is why. So resolving power is wavelength divided by diameter. Okay, in classical terms. I'm going to turn this upside down because I think bigger numbers, means better. So let's go with that. Hubble Space Telescope, 2.4 meter mirror. If it's observing 1 micron, I'm going to say it has a resolving power of 2.4 million. Right? As I said, it's actually the reverse, but I've put upside down. The Green Bank Telescope, it's the biggest steerable radio telescope in the world at 100 meters across, and if observing near the hydrogen line at 20 centimeters, it will have a resolving power of only 500. That doesn't sound very impressive. So what can we do about that? All right, so rather than build one big telescope, we build smaller telescopes and spread them apart. So they have basically the same effective size, at least to the extent. Okay. So the SK Mid Telescope, for example, will be a 150 kilometre sized dish. Think of it like that. So at the same 20 centimeters that we just talked about, where Green Bank has a resolving power of 500, the SKA will have a resolving power of 750,000. And then SKA can go up to 15 gigahertz, it'll have a resolving power of 7.5 million, okay? So poor old Hubble is only down at 2.4 million, so we've now got it covered. But there's a problem here, okay? We only have, in this cartoon here, we have 2 little telescopes. They're not very sensitive compared to this one big dish. We want collecting area. We all know that from astronomy. We want collecting area, big telescopes. So what do? Well, we put a lot of little telescopes together to make up that area, and then we combine the signals from those telescopes, and that's our interferometry. And that's what we're doing. And talking about interferometry is sort of a whole other talk, another topic, but basically we combine pairs of antennas, we combine the signals, we do some Fourier transforms, here's the dragons, we hide the details, and hopefully we come up with a nice image. One of the advantages of SK is that the sheer number of dishes we're putting in there will make this a lot easier to do. In the past, our arrays have been small in terms of number of elements within them, and so there's a lot of gaps in our coverage, and that's been a problem. Now we're getting rid of the gaps. And then why a square kilometre? So there are a bunch of folk going back to the 90s or so who said, look, this is the sort of collecting area we need to do the science we need to do in studying the hydrogen universe, okay? And so it's a collecting area of all the telescopes. That's not how they're laid out on the ground. I've already said they're 150 kilometres apart, but it's a collecting area. But in phase 1, SK Mid will only have a collecting area of 33,000 metres squared. So it's a starting point, okay? You can, if you're interested in the history, you can go online and get this book for free and have a look at it. It's just been published this year. But SK Mid and SK Low compared to other telescopes will be fabulous. So this is low up here. These circles are relative to collecting area. It's almost half a kilometre squared, so it's great. Compared to all the low frequency stuff, it beats them hands down. Mid is pretty good, 33,000. So the only instruments that are comparable here is, say, this big FAST telescope, 500 metre dish in China, has a larger area. The rest aren't in there. So. And SK, it's really a big data machine, and this is one of the issues that we're trying to deal with now, is how to process all this data. So I've just put this up. If you are into these sort of numbers, You can see we start with petabytes and we go to terabytes, and then we've got to push this terabytes down across these massive links to these data processing centers. So basically, that thing that says CSP and then the other thing that says SDP, they're supercomputers required to process the data. That's a major problem we haven't solved yet. Now, let's talk about some of the science. One of the big questions to do hydrogen universe is how do galaxies form and evolve? Okay, so here's a beautiful montage of images in hydrogen at the actual physical size of them from a survey with the VLA. And this is cartoon is supposed to motivate you for why SK will be fantastic. So the two images there, it says observed H1, okay, they're actual observations similar to the ones in the background. So these are actual observations similar to these. And these are simulations done on a computer by people thinking, well, this is what the galaxy should look like if we could see all the low intensity emission. SKA will produce images like this, not just computer simulations. And that will help us understand how these galaxies are still accreting matter and gas from the cosmic web, from all the stuff in between them. We don't understand how that happens. So, all right, so let me take you through a little motivation here for why that's interesting. Let's see if we can go along. So on the left here is two plots of the same thing. Basically, we're showing rate of star formation on this axis, and just done in a couple of different ways, and time. So we're 0, looking back in time to the Big Bang. Okay, you can either look at it in billions of years, 4, 8, 12, or you can look at redshift, which we 1, 2, 3, etc. Basically, show that in the early universe, the star formation rate started to increase and increase and increase until about this peak. It's about 9 billion years ago. So, okay, and then since then, the star formation rate of all the galaxies has been dropping to this point. Okay, well, that's fine. That is what it is. Problem is, though, when we look at the galaxies and the amount of hydrogen gas in them over the same period of time, this redshift, they're flat. So what's happening? Stars form from hydrogen. If the star formation rate's dropping off or changing, why isn't the amount of hydrogen changing as the stars form from that hydrogen gas? That's a big question we don't understand. And one of the problems with these plots is that all this information we have covered in this shaded area and this shaded area here is from observations not at radio wavelengths. They're from optical and ultraviolet and infrared, and they all have problems. The problem is that the same we saw with looking at a galaxy, there's dust in the way. We can't see everything, so we have to extrapolate, make assumptions. If we do this in the radio, we don't need to do that. We just observe it all. So SK will be able to observe through this peak and down the other side and actually get the actual values here. And then the hydrogen gas here, well, this is all based on sort of assumptions. This is what we currently observe in the radio with our hydrogen, just this little bit here, not very far. We want to observe way over here, which SK will do. So we'll be able to tackle this question. Another part of the hydrogen is what happened in the early universe when the first stars and gas formed. So starting at the top again is the birth of our universe, and it goes down to current times. So on the left you can see the time, and on the right the major events. We know about the cosmic microwave background, so the last bit of light that we can see from the early universe, and then the universe goes dark as it basically, instead of being ionized, it becomes neutral and no emission happens. And then sometime after that, 400 million years or so, the first stars, or the first galaxies, or the first something like that start to form. Basically through gravity starting to win, okay? And when these stars start to form, they start to ionize the gas around them. So you go from a neutral universe of hydrogen to an ionized universe of protons and electrons. And that's what we hope to observe with SKA, to understand when this dark age has happened. Okay, so this is the same plot, just put in sideways instead of up and down. And this is supposed to show now that SK low will observe this part from the dark ages right through the formation of the first supernova and black holes. And we'll make a movie of how that structure forms from nothing to structure, ionized structure, and galaxies at the center of these cosmic webs. And SK mid will carry on to look at normal galaxies in H1. So that'll be fantastic. Without radio astronomy, we wouldn't know of pulsars. Pulsars were discovered at Cambridge University, same month as I was born, basically, so too long ago for me to mention. But these are fantastic clocks, and this is the best one, 10 to the minus 18 accuracy in seconds. So pulsars themselves are interesting to people. This is how they arise. So basically this is the star formation life cycle. Interstellar cloud of gas and dust, parts of this collapse to form protostars. Smaller stars follow this path along the top. They live their life, they die, they become red giants, they shoot off their outer layers in planetary nebulae and left with a white dwarf. The larger ones, okay, they go into red supergiants when they die, and they die much quicker. They probably go supernova, and depending on the size of the original star, you're left with a neutron star, that's the pulsar, or you're left with the black hole. So these are dead stars that are made of neutrons. They're very, very dense. This is sort of the size of a neutron star, okay, compared to a city. Okay, they're only like 10 kilometers across or something like that, but they're extremely dense. So if I took neutron star material and put it into a baseball, I have another version of this with the cricket ball, which I should have used, but if you put into something that's a baseball size, okay, then it weighs about 20 trillion kilograms. That's in a baseball made of neutron stars. 40 times the human population, that's crazy. And we all remember from about 10 years ago now, the first signatures of mergers of black holes from stars, massive stars form. They sort of have this, they warp the space-time around them, and as they get closer and closer to merging, that space-time starts to really oscillate. And then when they combine, there's a ringing effect happens. It goes out through the universe, okay? Gets there, then there it goes, done, all right? And that was observed in optical, with these optical interferometers, okay, they're very sensitive to the changes in the path length along these interferometers, so they're very sensitive mirrors with lasers, and they can see this signal happening, so how the path length changes, and these two, all these signals show the ringing down, the merger, and then the aftermath. Okay, so that's what they do for the stars when they form when two black holes merge that are like stars, but. And that's great for testing relativity, Einstein's theory, okay? So the predictions from those match very well. In the radio, we do this in a different way. We'd use the pulsars as clocks and see how the clocks change if we put them under extreme tests of gravity. In this case, we want the pulsar to be near something that's really strong gravity. So another pulsar is great, but a black hole would be better if we could find these. We don't have any pulsars going around black holes yet. So here we have on the right here observations, all the red dots of a pulsar-pulsar pair compared to the predictions from General Relativity, and they are spot on, 99.9% agreement. But this is one example, and astronomers want more and more and more of them. So that's what SK, we need to find all the pulsars and find the best ones and do these experiments over and over again. Okay, so the merger of mass black holes, about stellar mass type black holes or a few tens of stellar masses is great. We're interested in observing the mergers of the supermassive black holes at the centers of galaxies going back into the early universe. So we're talking things that are 1 million to 1 billion times the mass of the sun merging. And how we do that is we time pulsars within our own galaxy. So when these two black holes merge, the wavelength that they put out is galaxy-sized wavelengths. And so we need to observe at galaxy scales to detect that. And so we basically will have a series of pulsars throughout our galaxy, which we've timed extremely well and extremely clean signals, and we use it as arms, as part of an array. And we measure the changes in their timing, changes in their pulsars to infer black holes. So that's sort of being done. There's a lot of work being done over the last 15, 20 years with instruments in North America, Australia, China, and Europe and India here. And this just shows basically the predictions is the dashed line, and then all the data are the plots. The data are the sort of numbers, are the up and down signals here. This is hinting that they're starting to detect the background. They don't prove it yet, but they're starting to detect it. SK will nail this, and it will also detect individual events. So we'll be able to say where the black holes are merging, not just that there's black holes merging. It'll be fantastic. Another thing that came out of radio in the last 20 years is fast radio bursts. Okay, so extreme astrophysics. They last about a millisecond, so they're 100 times shorter than the blink of an eye, emitted a long time ago in galaxies far away. So they emit the amount of energy in that millisecond that a sun emits in one day. Okay, so we know about hundreds of them now. This is sort of another image of the sky to show where they all are. It shows that they aren't in our galaxy, because otherwise they'd be all in the center strip, but they're all over the sky. And the predictions are there's about 10,000 of these going off every day. If we were looking in the right spot with the right telescopes, that's what we'd see. but we don't, obviously. What are they? Well, here's a sort of a bit of a joke cartoon that there's many ideas out there, a lot of serious ones in here, and throw in, you can spot the ones that probably aren't too serious. Okay. The idea is we don't quite know yet, although there are some leading candidates. Okay, so that's some of the headline science for the first part of SK. So where are we at? Construction is well underway. So here is 2 stations of 6 laid out for the low telescope. So basically, what we're doing is put this wire mesh on the ground first to help with basically the emission from the ground. So the ground has dielectric properties, and we don't get into the telescope. And then we put the antennas on top, and you can see 2 of them here are completed at SK low site. And this gives you a better idea of the scale. So here's the very, very first one being put out in a very careful way, with a lot of photographers around as well. These are going off the assembly line much quicker now, but you can see what they look like. We have a couple of these actually at the observatory at Jodrell Bank. Pretty soon now, they'll start to be decorated with Christmas stuff. You can see that they're referred to as the Christmas trees. And there's one of the stations close up. It's fabulous looking. It must be amazing to go out to site in Australia and see all this equipment out there looking like that. That's the real thing. Yeah, that's the real photograph of one of the stations up close. Yep, exactly. And this is the very first sky image movie, actually, from one of those stations. Okay, so the stations themselves act like a telescope, but they have a wide field of view of the whole sky. So this is the whole sky. You can see the galactic center, Centaurus A, large magnetic cloud, Cygnus A, all rotating. And then when the sun comes up, it obliterates everything else. It's the brightest radio object in the sky, and it's going to appear, and then you won't see anything else except background noise. Okay, so it's just a demonstrator to show that one particular station was working. If we go to the next slide. But more recently, we had our first event where we had signals between 2 stations combined to produce a positive detection, basically. So first fringes. I'm not going to explain in detail what these 2 plots are, but basically if the signals between the 2 telescopes weren't correlated, this would just be a random noise plot, and this would just be dots everywhere. The fact that there's structure in those 2 show that we're correlating the signal. And so this is basically when these telescopes become an array, and we've really started. So yeah, constructions were underway. Here's the dish. One of the dishes being built in South Africa, the pedestal going up, the dish framework on the back, getting the surface laid on it. And then a big lift, put the dish surface on one of the pedestals. This is all happening in South Africa at that Karoo site. And then actually, let's see. I don't know if this will work, but I think there's sound in here. Where is this? Oh, do I need to, I think this might be YouTube. No, okay, so I'm not plugged in YouTube, so I'm not going to see that today, sorry. Yep. You can certainly look at the YouTube link later on. It's a sort of a 2 or 3 minute video of a first lift and how excited all the people are working on it are to be actually to see that happen. And there's the first dish, and you can see the landscape that it lives in. It's a very harsh desert environment. So we have some major milestones coming up. This year, we've got the first few dishes and antennas on the ground, which we call science commissioning, so make sure the things work. About 2027, we have a lot more of them on the ground. We can start to do proper science verification, we call it. So the 2 telescopes will be at least as sensitive as any other telescope out there at radio wavelengths. So we can start to do comparison results and really shake it down. And then towards the end of the decade, the mid and low telescopes will be the biggest and best out there by far, and we'll start to do real proper science. All right, so that's it. If you want to keep up to date, we have a magazine which we either send out, you can get online, and all the usual socials are out there too. So thank you for your attention.
Thank you. That was really fascinating. I obviously haven't been paying attention to radio astronomy for a long time, because last time I looked at it, everything was just a blob. But clearly, there's a certain amount of satisfaction that your resolution is outstripping all the optical.
It's fantastic to move on from blobology to real science.
That's right. Yeah. Okay, we have time for some questions. We'll ask questions in the room first of all. Then we'll go to Zoom, and then there's anything on YouTube as well. So if you're on Zoom, put your name or question in the chat, and we'll hopefully read it out.
Thank you very much. That is very fascinating. So my question is, what's the difference between using the dishes in South Africa and using the antennas in Australia?
Right. They're kind of similar in one way, is that the antennas in Australia are the receivers, and the dishes in South Africa, those receivers are actually in the feed. So let me go to an actual image. So in this image of the dish, okay, we have the dish reflector surface, right? And we'll use this from optical wavelengths. And then there's this, basically, this is, there's a secondary here, but just hidden, yeah, you can't really see it very well here, but just below this is all the receivers, okay? And so if you were to take one of those antenna from low, you could, if you had a big enough telescope, like instead of 15-meter dish, had a 100-meter dish or so, you could stick one of those at the focus and use it as in the focus. But we can't do that with such a large telescope and such low frequencies. So we just basically put them on the ground and they look straight up. And then we use, instead of focusing the signal onto them from a dish, we use electronically, we use electronics to steer them and to combine the signals in that way. So they see the whole sky, it'd be great if we could actually focus the signal onto them, but because of the way nowadays with electronics, we can actually make them work like a dish in some sense. Back in the old days when Jocelyn Bell, for example, discovered the pulsars and stuff, you couldn't do that. You just had to put up the wires and hope for the best in terms of the lengths and stuff. But now we can compensate everything electronically in that way. Yeah.
Thanks for your talk. Early on, you showed a picture of M33, and you're looking at it kind of face on, but yet you could detect it seemed to be sort of rotating. So some of it was coming towards us and some away from us. And I would have thought, yeah, it would rotate like that. And I was puzzled by the fact it had a component of rotation the other way.
So if it was actually exactly face on, you wouldn't detect that.
Yeah.
Okay. But the fact that you can detect it says it's tilted in some way. And you could work out that tilt actually from the velocities. Yeah.
Simple basic question from right at the beginning. Why 408 meg? Not 409 or 322 or any number you can think of.
That I don't know the answer to. Why they chose that actual frequency at that time. Yes. I'm sure it has something to do with what electronics and systems they had available and what they could actually, it probably has something to do with what equipment they had available at the time and what frequency gave them the best sensitivity at the time when they did that work. This is stuff that was done 50, 60 years ago, something like that. Yes, because by observing at the different radio frequencies in the continuum, we do learn different information about what's happening in the space. So if you go to those lower frequencies, you start to learn about how the electrons are moving relativistically around magnetic fields. So whether it's 400, whether it's 500, often it depends on the equipment you have, not just the frequency that you observe at. But the exact answer for 408, I will go find out. I'm sure it's there somewhere.
Hi. The flat graph of hydrogen over time, how is it able not to just decrease throughout time from stars burning off the hydrogen?
That's the problem. That's what we want to solve by observing the actual hydrogen, not inferring the hydrogen from other means. Like why is the hydrogen basically flat? So if we observe in hydrogen and observe to very low sensitivities, we start to see the hydrogen emission way out in the suburbs of these galaxies, right? So what we hope we might see is the prediction is that basically these galaxies are still accreting gas from the intergalactic medium, from the cosmic web. They're not these isolated island universes. They are connected and the gas still flows in, so they can replenish the gas that's used up. That's why it's flat. That's what we think. We need to prove that.
Hi, thank you. You showed the tunable frequencies of both arrays. What's the bandwidth of both systems, and how does that correspond to how much redshift you can capture in a single accumulation?
So the bandwidth is basically the frequency range there. So for the low, this 300 megahertz is the full bandwidth. And then for the mid, we can't observe 350 megahertz to 15 gigahertz with one receiver. So we do have 5 receivers to do that. And each of those receivers, well, most of those receivers can cover the full bandwidth that they're sensitive to. So sort of at the lower frequency end, they'll have a bandwidth of about 1 gigahertz at 1 gigahertz frequency. And then at the higher end, when you're getting up to like 15 gigahertz, they have a bandwidth of about 2.5 to 5 gigahertz. So you can observe a lot of redshift in that, absolutely.
And so what is the range of redshift? Can you... Well, I guess you can do it for the galaxy rotations, but looking back through time, what's the variation in time you can get out of a single?
Well, for example, with the hydrogen line, 1.4 gigahertz, we can obviously observe at 1.4 with zero redshift, and then we can observe down to 350 megahertz. So there's that dish array, and that's the redshift of I think 2 or 3 or something like that. And then the low telescope takes over, it takes that redshift to 2 or 3, and it can actually push it all the way down to 20 or more if we want to. But we don't want to go really that far down all the time.
And in the images you're showing, what's the sort of exposure times, as it were, for those? What's the collection time to get all that data?
For the radio images? So for something like those radio images, you might spend... for example, let's take the VLA, which is the best interferometer in the world at the moment, or it was until Meerkat came along. You would probably spend a day. So in order to do this interferometry, you need to basically track a source almost as it rises, almost as it sets, and use the rotation of the Earth to compensate the fact you only have 2 dishes, for example. If you have 2 dishes, you want the Earth to rotate so you can fill in some of the space just by the Earth rotation. So you're not limited much by sensitivity, you're limited by how much you want to fill in the gaps, unfortunately.
Fantastic talk, really enjoyed it. With your static arrays, how do you know where they're looking? Do you switch between them? Do they have a...
You said the static arrays, like the low telescope that doesn't move.
Yeah.
Yeah, so that's all done through electronics. So basically we can make them point. Okay, they see the whole sky, but we can make them point by making the signals between pairs interfere constructively, basically. And we do that by putting an electronic difference between the signal paths. Focusing.
Yeah.
And by doing that, you can make them move around the sky. Yes.
Yeah, and with the movable array, are they all looking at the same point in the sky, or are they looking at different points in the sky at the same time?
Depends on the science.
Okay.
You can make them all point at the same spot, and you get the maximum sensitivity, and that's probably how we'll use them most of the time. Or you can use some of the array to point in one place and some to point another place. It kind of depends on the science. An example is that for the mid-array, I said that about half the dishes will be in a central area of about 1 to 2 kilometers across, okay? That's great for the pulsar people because they want them close together. They want sensitivity, so they'll probably just use that, and they'll ignore the stuff on the arms, right? Other people want very high resolutions. They want to use all the stuff on the arms and in the center to do that, so it kind of depends on the science, yeah. But they can be pointed independently. Yep.
The last question, promise. With your Doppler imaging, when Doppler's wonderful when things are moving straight towards you or straight away, you get the correct velocity. But when it's moving at an angle, you don't get the correct velocity.
No, you just get that along the line of sight, yes.
Yeah. So how do you compensate for things moving at different angles?
Hopefully you have some other information to tell you what either inclination, we talked about before, they have an inclination, so you can compensate for that. So you need some other information to figure out how to actually compensate for the fact that you don't have them just coming towards you or just going away from you. Yeah.
So you're using optical information or other radio information?
Absolutely, either, yeah.
Okay. Last.
You okay for a few more? Because you've clearly converted some optical astronomers to radio. Yes. If you're okay, it's fine.
Yep.
Thanks very much, Tyler, for a fascinating presentation. I was wondering, I noticed that the site in South Africa and the one in Australia are roughly on the same southern latitude. Is that important? And could you, for instance, put a third southern hemisphere site somewhere in South America? And for that matter, could you add sites in the northern hemisphere to the whole network?
Right. So the two sites in Australia, they're chosen for a few reasons. One key reason is that they're very quiet in radio terms. There's no people around. There's a slide that shows that in Western Australia, for example, the site, there's more sheep there than people, right, by a large number. Like, there's no one around. But the latitude is also important because when you're observing at this sort of 33, 35 degrees south, you've got the galactic center going directly overhead, which is important. And then the Magellanic Clouds are also obtainable. So there's all those three winds, basically. Yes, you could probably put one in South America. That's where the ALMA large array is up at very high altitudes because it needs to see through the atmosphere. You could certainly put stuff there. In the US, there's a very large array. In the UK, there's the E. Merlin array, which is sort of 6 dishes on the same size scales as MID, but only 6 dishes, right? So there's definitely reasons to put them in the north as well. And in fact, the US are going to build what they call the next generation VLA, or they're hoping to build it if they get all the funding. And they will put that basically starting out where the VLA is on their site, and it'll be like an SK, but even higher frequencies. And maybe we can work together in the future.
Shall we give our Zoom users a couple of questions? Nothing on there? Okay, we'll just on there. Okay, last one here then.
Yes, thank you. Given, following on from the Y405 megahertz or whatever, that's a very specific frequency. Do we know anything about what we're losing? You know, either side of those, in the sense of, it's sometimes useful to be able to see a continuous spectrum, and yet in radio astronomy you've got these very tight windows dictated by the technology.
Yeah, absolutely. So certainly back when those data were taken, the technology probably only allowed for quite, even though it's continuum, quite narrow sort of bandwidth. So I'm going to guess a few tens of megahertz at most, maybe back then, right? But for example, the SK mid telescope and its lowest frequency band will cover 350 megahertz, so below the 400 megahertz, up to somewhere above 900 megahertz. I don't remember the exact number. So there's about 600 megahertz. It'll be able to observe that simultaneously. So there's a massive spectrum range that we'll be able to cover in one observation. So yeah, we are now getting the information. As the technology catches up, we can cover more bandwidth simultaneously. Yeah, very important. That image I showed, the galactic center from Meerkat, is color-coded just in that way. It shows the different spectral indices, basically, so that's how the frequency changes. Yeah.
Thanks. You kind of glossed over your data capture and all the hardware involved in trying to pipe all this stuff to some place where you can do something useful with it. Are you laying huge fat fiber cables into Western Australia, or what? How does it work?
Right. So you see that there's these. So fiber is being laid. At the moment, a lot of it's dark fiber, so it's just going in the ground. We were planning to have the first supercomputer processors basically on site, but now it's become cheaper and more efficient to actually just flow the data down to Perth and Cape Town to process, rather than trying to build these facilities on site. So yeah, basically large spigots where the data is pushed down, but we want to process as much before we actually pipe it down. So we're trying to do that on site, but then a lot of the work is done off site. At the moment, a lot of stuff is still being worked on in terms of what it will look like, actual hardware, and how you're going to do it. My wife's trying to dodge back there, but this is sort of area that she sort of works in, or is starting to work in, so at some point soon she'll know more about this than me. That's necessarily kept fuzzy because I don't think we've shown that we can scale up yet, so we're still working on that. We can still process little bits of data on the current facilities, and we know how to do that. And we're trying to show that we can do this on this large amounts of data. We haven't done that yet. But we need to do that soon because 3 or 4 years we're going to have that sort of data. Sorry, say that again? We've talked with them in the past, yes. Yeah, exactly. And that may, we'd like to be away from this, as much away from those sort of services as possible because of that issue, but we may have to do some of that. Another aspect I didn't touch on is how you run these facilities. What sort of power do you need? Okay, so we're talking a few megawatts on each site. Okay, so one of the problems there is, well, that's a lot. What do you do with that? So in Australia, the mining companies are out there. They're using a lot more power than that, and they're using basically diesel, right? Which is not good. Okay, so we're trying to our target is to be green. But we can't do that initially all the time. So, for example, we're trying to power all the telescopes out on the arms through PV, so photovoltaic cells, basically. So they'll be standalone systems, and we can do that now, but we can't do that in the core. So initially, the core will be on both telescopes will be done either through like diesel generators or a grid we'll put out there. But we do want to go to a green system, and that's something where we may have to buy that sort of stuff from a big supplier. Yeah.
Do you have anything on YouTube, Will?
One question. We've got a question on Zoom, if that's okay.
All right.
Ron, do you want to?
Just a second.
Yeah. Yep, excellent talk there, Tyler. It's really fascinating. We've got one question from Gregory McNiff here, and you mentioned about pulsars and about, I think there was a bit of mapping for black holes and stuff like this, but he really asked, can you discuss how pulsars can function as a celestial GPS? And I suppose to enlarge on that is, what would you see? And I suppose, what would you see as their potential use in the future with pulsars, or have we sort of
okay, I'll try and answer what I think is the question here. Because we can measure these timing signals so well, we can actually position them within our galaxy quite accurate too, if we can observe them, if our facilities are sensitive enough. And so to date, we've just been able to see basically the ones that are kind of near to us. The idea with SK is you'll be able to see pulsars across the whole galaxy. Okay, so you'll be able to map the galaxy through pulsars. Okay, a lot of the work that's been done now has been through stars and through what we call masers, which are like lasers but microwaves. Again, they're very bright signals that come from very small regions, so we can really figure out exactly where they are, and pulsars have that same property, although not as bright. And so at least in our own galaxy, they'll be great for mapping. And the hope is that we'll start to really see more of them in other galaxies, okay, and start to do the same sort of work. I don't know the details of or the prospects for that, but certainly that's what the pulsar community hopes to do in some of the closer galaxies. Yeah.
Have you got one for Zoom? Yeah. If we can, just one more from Zoom, and then we'll finish, if that's all right. Yep.
Yeah, it's a question from Ron Morley. Ron, do you want to come off mute and ask your question?
Yes, I've come off mute. Yes, great talk, Tyler. Thank you very much. That was excellent. I'm afraid my question is an engineering one. The Christmas trees in Australia look quite frail. Have they got good roots? They don't get blown away in sandstorms and other things like that. Bearing in mind our dreadfully changing climatic conditions across the world.
Exactly. Even in Australia recently, we've had some out on site. There's actually a big flood channel that we've had to deal with, which we knew about before, so we didn't put any antennas there, but it's been a major problem for construction. So yes, we've had test arrays on site. 1, 2, 3, at least 3 different types of antenna designs and ways to secure them in Australia. So the final design now, the 4 feet are secured to the wire mesh and the central pole as well. Okay. Some early designs included having a massive concrete ring base for them. Okay, was one, but that's a lot of weight and didn't work very well. So over the time, we've tried different ways out, and this looks to be actually working quite well. Like the current design of really getting them tied down to this ground plane. And there is some early designs where there was no ground plane, so that was a big problem. That's why we had these ideas of these concrete pads, and there's some great images of those online you can probably go find, but thankfully we didn't use them. Yeah. So I think we're good.
Very good. Thank you.
Yeah, the dishes are much easier. So I don't have any pictures of the foundations, but the foundations are really quite deep, with many structure points, many bolts, and yeah, so they're pretty good. Yeah, they'll be fine.
Well, thank you again for your patience for all the questions. We've clearly
not a problem.
got a lot of interest there, and thank you for your excellent talk. Can we thank Tyler again?
Thank you.
Okay, Sean is now going to tell us about the sky in October, but this will take us a minute or two to switch over because it's coming remotely. Sean, if you want to share your screen on Zoom and give Jim a few minutes to press the right buttons. Yeah, okay, go for it, Sean.
Okay, well, good evening, Edinburgh. This is the votes of the Irish jury. Square Kilometre Array, 12 points. Based on that presentation. It's lovely to be with you all this evening, albeit remotely. I'm sorry I can't be with you in person. I've had a number of health challenges in the last couple of weeks, which means I'm coming to you from Ireland. And forgive me if I sound and look a little unwell, but I've, on top of everything else, got COVID at the moment. So my apologies for any coughing or spluttering or anything else that might happen during the presentation. And if any stage the link drops out or anything freezes, maybe someone can message me and let me know. So October 2024, October is probably a good month in which to found an astronomy society, because the clocks, as we all know, go back in October across the UK and Europe from daylight saving time to standard time. So perhaps it's appropriate that we're doing this presentation in October, and that October is our centenary, but more on that later. As ever, I want to start by acknowledging the fantastic work of our esteemed colleague and former past president, Alan Pickup. Alan has now been producing his Sky This Month article for the Scotsman for 50 years now, I believe, since August. It was his 50th anniversary in the Scotsman. If you haven't seen it or haven't read it, please do. It's a wealth of information. You can find the link to it on the front page of the ASE website. These are indeed Alan's star charts for the month of October. You'll see there, this is taken directly from Alan's article. These maps show the sky over Edinburgh at 11 p.m. On the 1st of the month, 10 p.m. summertime, that is, on the 16th, and 8 p.m. back on GMT once the clocks go back by the end of the month. And we'll look at those in more detail now. So, looking west this evening from Edinburgh, just about now, in fact, about 20 minutes ago, you can see that the constellations we're used to in the summer sky are now descending well into the west. The brightest object in the west at the moment is Arcturus in the constellation of Boötes. And so that would normally dominate the summer sky, but at the moment it's down low in the western sky. Looking at the same position a month from now, so back onto GMT, you'll see that it's now off the southern sky altogether, and the summer triangle is now setting down in the west. You can see Vega here, Deneb and Altair, and obviously the arm of the galaxy arcing overhead. Looking north tonight, we've got Ursa Major is getting to that point in the evening sky where it's now low in the northern sky. You can see the bright star Capella starting to rise out of the north, and you'll notice tonight, just around now, the first of Taurus in terms of the Pleiades cluster is starting to come up over the horizon, and that'll play an ever increasing and more interesting role during the month. Looking north by the end of this month, you'll now see how things have moved along. Gemini is now coming into view in the evening north sky. And from an evening point of view, Ursa Major is now at its lowest point in the northern horizon. Looking west this evening, you'll probably notice the most prominent feature in the eastern sky, I beg your pardon, the eastern sky over Edinburgh at the moment is Saturn, which has been putting on quite a show in our sky for the last couple of months and will continue to do so for a while. We've got, of course, Andromeda, which is a lovely feature to look at in the evening sky, and I'll talk about that more in a little bit. By the end of this month, we've also got Jupiter making an appearance on the horizon, and that's also going to have some very interesting things. You'll see it's contained within the constellation of Taurus. By the end of the month, this is looking east on the 31st of October at 8:30 p.m. And so this makes for some very lovely objects in terms of both binocular viewing and our astrophotography towards the end of this month. And then looking south this evening, just about now, you've obviously got Saturn in the southern sky in Aquarius. You've got the center of the galaxy in Sagittarius now starting to dip down under the horizon as we move through the month. By the end of the month, you'll see it's effectively gone. It's been replaced by Pegasus in the southern sky, and Saturn is directly to the south of us. So, what else is happening in the sky this month apart from just the ordinary things that we would expect to see? Well, for those of you interested, this is the Purple Mountain Observatory in China, or Shushishuan, as it's apparently pronounced in Mandarin. And this has given its name to one of the more prominent comets around at the moment, the Shushishuan Atlas comet, which has just now passed behind the sun and is coming back into the western sky. I think this was probably best observed from the southern hemisphere. I found this rather nice photograph online taken by Jordan Cantello from Perth in Western Australia just a few days ago. You can see the comet emerging up out of the evening sky, and it's obviously a naked eye object in Australia. Alas, not here in sunny Scotland. This is an image from the BBC Sky Tonight magazine showing the comet in all its glory. And again, you'll notice that was taken from Namibia. Again, slightly clearer skies than Scotland. So probably a better chance of imaging that particular comet from the crystal clear skies of the Namib Desert. But if you are interested in trying to see the comet, then it's, as I said, emerging up out of the evening western sky, passing through the constellation of Ophiuchus or Ophiuchus, depending on how you like to pronounce your snake handlers. But it's low in the western sky here, and obviously as it's moving away from the sun, it will start to diminish in magnitude, which will probably make it more difficult to observe. By the end of this month, it should be around magnitude 6.1 at a distance of, there it is, at a distance of about 0.97 AUs from us. So by all means, for those of you who are more skilled and have access to some excellent equipment, then you should try and have a look out for that. So on to some other things. Again, this is taken from Alan Pickup's excellent presentation on the sky in October. These are the phases of the moon for October. You'll have noticed in the cover slide for this presentation, it showed the annular eclipse, which took place over southern South America and indeed Rapa Nui, formerly known as Easter Island, which should have been pretty spectacular. Just 2 days ago during the new moon, pardon me. The moon, of course, is at its farthest from the Earth at that point. That's why we had an annular eclipse, or a ring of fire eclipse, as the media like to christen it. First quarter, as you can see, is on the 10th, full moon on the 17th, and the last quarter is on the 24th. The moon is not very high in the sky in Scotland this month, but it does present some interesting objects for observation, which I'll come on to in a minute or two, one of which is a conjunction with Saturn. So on the 14th of October, in the evening of the 14th of October, the moon is going to pass right next to Saturn, 0.1 degrees north of Saturn. This is going to be in the southeastern sky, in the constellation of Aquarius. So hopefully, weather permitting, that's a target that might be worth looking at. It could be good for imaging as well, but again, all dependent on the weather. Speaking of opportunities, we've got 2 meteor showers this month in October. The first, of course, is the Draconid meteor shower. That reaches its peak overnight on the 7th to the 8th of October. That's early next week. Unfortunately, I don't think the weather is going to play ball with us in Scotland early next week. It might do, who knows, but I don't think so. But if you do have an opportunity and it is clear, then looking out to the southwest towards the constellation of Scorpius and the bright star Antares, that's where you should see any meteors emerging from. Under ideal conditions, you should see hopefully around 10 meteors per hour. Obviously, you've got the crescent moon in that vicinity as well, in the 7th and the 8th of October. So depending on how bright that is, of course, that may detract from some of that, but it might also present some really interesting photo opportunities for the more skilled among us. The second meteor shower is the Orionids. And of course, famously, the Orionids exist because of the trail of debris left behind by Halley's Comet when the Earth passes through that trail every October. The greatest number of those are expected to be seen around the 20th and 21st of this month. But we'll have a gibbous moon at the time, so it could be quite difficult to see many of those. But again, under ideal conditions, you're looking to above the club, the arm of the constellation of Orion for the radiant point. And if you're lucky, you may see up to 20 meteors per hour. But again, that's obviously preying on luck when it comes to the Scottish weather. So moving on to the planets in October, what's happening with them? Well, so tonight, this is for the 4th to the 5th of October, so tonight into tomorrow morning. Really, the only naked eye planets that are observable in our skies for this month are Mars, Jupiter, and Saturn. Mercury and Venus are very low at the moment, or just emerging from behind the sun. So they're lost in the evening glare, unfortunately. But all of the other planets do make for good observing this month. By the end of the month, again, it'll predominantly be Jupiter and to a lesser extent Saturn, and Mars is a morning object. As I was saying, Mercury and Venus are no show at the moment, so there's not much point lingering on their presence or lack thereof in the October sky. But Mars is obviously making quite an appearance in our sky at the moment, and it's going to pass quite close to the twin stars of Castor and Pollux in Gemini on the around about the 14th and 15th of this month. So that's something to watch out for if you're interested. Looking to the east, probably in the early morning would be best, and again, weather permitting. Mars could make a good observation point there. We'll come back to Mars again towards the end of the presentation, as there's an interesting little aspect I want to point out in relation to the Society. As for the king of the planets, well, Jupiter is becoming more prominent now in our skies. It's appearing in the eastern sky in October, and it will continue to rise through the month into the southeastern sky. There are some really good opportunities to see Jupiter as it's passing through the constellation of Taurus. So it'll be passing quite close to the Pleiades. star cluster, and of course the red supergiant Aldebaran, which is the red eye of the bull of Taurus, so in between the horns of Taurus. The moon will also be in that vicinity on the 18th and 19th of October, so that should make for some interesting viewing around the middle of the month. Similarly with Saturn, Saturn this month is in the southern sky, as I was saying, southeastern sky. It was at its closest point to the Earth on the 8th of September. It's now obviously moving away, and on the 13th and the 14th, it will be passing close to the moon, or at least it'll be in the same region of the sky as the moon. So that, as I've mentioned earlier, there's a conjunction there. So that should give a good opportunity for those interested in viewing both together. So what else is happening at the moment? Well, as members will be aware, this is our centenary. And one of the things we've done with our centenary is the establishment of our remote observatory in Spain. And this has given our members opportunity to take lots of fantastic images, which otherwise might be difficult to, practically impossible, to take from Scotland. So I've just pulled together a short selection of a few of the nicest images I've seen online with our new Acero imager this month. Pardon me. The first is from our colleague John Biggs, and this is an image of dark nebulae, Bernard 312 and LDN 379. That's in the constellation of Scutum, which is near Sagittarius, if my memory serves. And that was imaged back in August with the Dalrada, which is one of the two instruments we have at our remote facility in Spain. This is a beautiful image from our colleague Ian Smith of the Ghost Nebula in Cassiopeia. Again, taken this time towards the end of September. And this was taken using the Murrell telescope, which is the other telescope that we have in Spain. And in fact, John Biggs also, I think, had a very lovely image also of the Ghost Nebula in Cassiopeia. So if you go onto our Flickr site, you will find all of these images, but I liked Ian's image here very much. Matt Finch took this beautiful image of the open cluster in Andromeda, the Aveni Hunter 1. Again with the Murrell around the middle of September, and I think it just shows you just what an opportunity the remote observatory is for our members to be able to take really excellent images of the sky and share them with the public. It's really added to our ability, both for members and for the general public, I think, of the society. Robert Arnott took this lovely photograph of the Skull Nebula in Cetus, again around the middle of September, and that was taken with the Murrell telescope. There's one or two images of the Skull Nebula taken by other members on there as well. I wasn't particularly very familiar with this nebula, I have to say, until I was preparing for this presentation, and I think it's another one of the joys of having a facility like this, is that it introduces you to all sorts of deep sky objects that, even though I've been looking at the sky for the best part of 50 years, I still wasn't aware of. One of my favorite things in the night sky, and one of the things I think that most people love to look at, is M31, the Andromeda Galaxy. Our colleague Jonathan Cow took this with the Dalrada scope. Beautiful, really, really beautiful image, clear image of Andromeda, our closest galactic neighbor, if you exclude our Magellanic hangers-on. So that's a really lovely image. Mike Christie took this image of the galaxy NGC 7331, which is in Pegasus. And there's actually a cluster of galaxies. I think it's often referred to as the sort of the 7331 cluster. The galaxy itself, which is obviously the large spiral galaxy you see here, is about 40 million light years away. But if memory serves, I think the rest of the cluster is something like 300 to 400 million light years away. So it's a cluster from our point of view.
Again, with the Merle instrument, and it's a testament to our esteemed colleague from whose donation we financed this instrument and the great work that it's now doing in collecting images. And finally, I picked this image from Pat Devine of the clamshell emission nebula in Cygnus, again with the Dalrada. That was imaged in August of this year. So it just goes to show that even during the summer months in Scotland, when the sky never gets dark, thanks to our new remote observatory in Spain, members can now do quality astronomy all year round, regardless of the weather conditions, local weather conditions in Edinburgh. There's I should say, another very lovely image of the clamshell nebula on our Flickr website this month. I think also by John Biggs. If I've misattributed that, apologies, but I think John has one there. But I particularly like this one from Pat of the clamshell nebula. So that's all our images for the moment. I briefly wanted to turn to our birthday. Happy birthday! So I'm honored to be doing this presentation in October of 2024 because it's 100 years this month since our society was founded on Wednesday, the 15th of October, 1924. So on that date this year, we'll be 36,525 days old. Don't we look young for our age? So what's changed, I hear you ask? Well, for a start, the sky has changed. Many things have changed, but the sky has changed. But I thought it'd be interesting just to look back and see what was the night sky like on the 15th of October, 1924. And it turns out it was like this. This is looking south from Edinburgh on the night of the 15th of October, 1924. And you'll see the most prominent object in the sky at that time, apart from the waning gibbous moon, which was rising here in the southeast. But Mars was quite prominent in the southern sky at that month, at that year. It was quite bright, actually. It was around 1.54 magnitude. And this image was taken in 1924 from the Lovell Observatory in the USA by none other than William Wright, the famous astronomer who went on to become director of the Lick Observatory. And this was the best image that you could get of Mars in 1924 with one of the most powerful optical instruments on the planet in 1924. As you can see, it's a fascinating image. I suppose to the modern eye, it kind of looks like a slightly misshapen lemon. But certainly to astronomers in 1924, it was quite a startling image to be able to take. Fast forward 100 years, and what can we do now? Well, here's a series of images taken just 4 years ago by our current president, Mark Phillips, using his own instruments from his home in Edinburgh. And there's a sequence of photographs of Mars here showing the various climactic zones, showing the rotation and the changes to the dust clouds, and indeed the various main features on Mars. And that led me to think, I suppose, how far we've come in terms of astronomy, public astronomy in the century since we were founded, that I use the word amateurs lightly because we have many professionals in our society and many people who, while by name might be amateur, they're de facto professional photographers when it comes to photographing the night sky. The images they're able to take today compared to what professionals could only dream of 100 years ago is really quite astounding. So it made me wonder what might happen if we ever get to the point of celebrating, or our successors get to the point of celebrating ASE 200 in 2124. Will we be on Mars? Well, I won't. I won't be here. In fact, at the moment, I don't feel like I'll be here much longer. But I certainly won't be. Will humans? I'm not 100% sure, despite the best efforts of Mr. Musk and others. Our technology certainly will be, but whether the human body will be able to last long term in a a low gravity climate like Mars, I'm uncertain. But it could quite be possible that within 100 years from now, amateur societies like ours routinely have observing equipment off-world, based on other worlds. It sounds like science fiction now, but to the scientists in Lovell in 1924, what we do today, the fact I'm speaking to you from 600 miles away, is complete science fiction to them, or would have been. So maybe in the year 2124, someone will be imaging Earth from the surface of Mars, use our successors using one of our future devices. I hope they will be. Either way, I hope the society will be around in 2024. So that's all from me for the moment. I hope you had a really enjoyable evening, and I hope you enjoy the rest of the time there. I wish I could be with you, and I hope to be back with you again soon.
Thank you, Sean. I think John Briggs would like an R in his name. Robert Arnold might like the end of his name changed slightly as well, but very good. Thank you. Excellent. Thank you to Tyler again tonight, and for your patience with all the questions. And thank you, Sean. Thank you to the tech team. And there's tea and coffee at the back. I hope to see you again here soon. So good night. Thank you.